All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let me make sure that I have everything set up here. All right. So before we get started, it means the second day of class, which is kind of like a week in a regular semester. We literally had 3 classes yesterday, but I don't even know if I can say, oh, it looks like everyone's here, because I don't really know if everyone's here. I read over your questionnaires and it seemed to me like some of you are out of place. Like this is might be the wrong calculus class for some of you. And I asked you guys to like talk to your advisors and stuff. So if you're in the business school or you're in pre-health, this is not the Calc 1 that is recommended for you guys. So if you're pre-health, so if you're like a biology major, you're interested in pre-med requirements, etc., you should be taking Math 1203. And if you are a business major, the Calculus 1 you should be taking is 1109. So essentially you learn about the same things, but there are minor differences, and you would not learn about doing those things on different types of functions that you would hear. For example, trig functions. So in this class, we will be looking at doing calculus with trig functions, whereas in the other calculus classes, you don't touch trig functions at all. So there are some significant differences between the 2 calc classes. And I would say that this one, 1206, covers more material, and I would tend to explain more of the background to things. So the lectures are also going to be at slightly a higher level, although I'm pretty sure everyone should be able to follow along reasonably well, or else I wouldn't do the lectures like that. So yeah, there are some significant differences. So make sure that you are in the right class. Second of all, I sent another email for you guys to let me know if you're receiving all methods of communications for me. So last week or a couple days ago, I sent out communications through like 5 sources or something. And I just want to make sure you got all of them. So be sure to reply to that email if you did not get something. If you don't reply, I'm just going to assume you got everything. So just let me know, oh, I didn't get an email from this, or I didn't get an email from that. And let me just know, because there are a lot of things that are super important. So Jupyter is very important. So if you didn't get an email from Jupyter, that's super important. Gradescope is very important. If you didn't get an email from Gradescope, that's super important. And I suppose it's kind of important if you didn't get an email directly from my email, but for the most part, I'll probably be using Jupyter to mass email you guys in the future. So yeah, make sure you know everything. You got everything. So that's another thing I wanted to say. What else did I want to say? I think that's it for now. I guess we can start with any like general questions. I know it's the second day. You guys might still have questions that you've thought about over yesterday, last evening. Are we good with everything? Okay, all right.
I have one question. Sorry,
yes.
I switched into this class. I'm Miles. I accidentally signed up for July Calc, but I should take it now. And
okay.
So with yesterday's class, is that recording available for me to?
Yes.
Okay.
And okay, give me a second. So I am going to paste the link for the class webpage in the chat.
Thank you.
And that is kind of a central hub. Like it'll have links to everything else. So if you just registered, you probably didn't receive anything so far other than the Blackboard message. But just make sure to check in with me to make sure that I have you signed up for everything you need to be signed up for. Is there anyone else new? Okay, so I also, today during the break, I'll be taking attendance again, and then I won't do it after that because I'll have to make a report on who's attending and who's not for, financial aid reasons and just to know if students are showing up. But in general, I'm not going to be taking attendance, and I'm not going to be giving credit for attendance or anything like that. I do recommend you show up. It's very important. Chances are you will do worse if you don't, but it's not, strictly speaking, a mandatory requirement. That being said, I left you guys with some problems to try. I don't know if you guys managed to try it. So let's get to those. Let me make sure I can see the chat, and yeah, everything looks good. All right, so bunch of examples that we want to get through. So conceptually, I think we did overkill here, but it's nice to do a lot of examples to kind of get your algebra skills greased up again. It might have been a while. So some of these, the lessons will be repeated, which is not a bad thing, but I want you guys to get good at like solving problems. So we're going to do a bunch of examples. And let's get to it. So we learned about exponentials and logarithms last time. You know all the rules, you know how they work, you know about their graphs. You know how they relate to polynomials and power functions. So now let's actually just look up straight up solving some problems. So problems that you might encounter on a test. Okay. So yeah, let's do that. So let me maybe copy problem 1. Okay, 1. All right, what is this? What did you guys get? Yeah, you guys can just go. Like, I don't think we're ever going to be in the situation where like everyone's tripping over each other to answer a math problem. Like, it's never happened yet. I don't know if you guys are going to surprise me, but it's never happened, like ever, where it's like, oh, and everyone's shouting over each other. So yeah, if you think you know the answer, just chime in. You don't have to like raise your hand and wait for me to call on you or anything. It's totally cool for you to just speak. Yeah.
I got 1/2.
Okay. How'd you do it?
Well, like, the e and the natural log like cancel each other out. So then I got -2.
So why couldn't I just do that and get -2? How'd you get 1/2 if the e and ln cancel?
By
the way, that's wrong. By the way,
okay.
What I just did is wrong. So I just want to make sure, because you said the e and the ln cancel. So I just want to say common error. Is if you have e to the minus ln of 2, people will be like, oh, Jhevon told us that e's and ln's cancel. So I'm going to like, and then I get -2, and that would be wrong. However, why is that wrong? Why wouldn't that be what I should do? What is the issue here? Because we know what the rule is. So the rule that we'd be applying, I think was rule 9 that I gave you guys yesterday, is that if you have a to the log to the base a of x, it just gives you the x. So it's like the exponential and the log kind of cancel out, which of course would mean that e to the ln of x is just x. So because you can see like the e and the ln would cancel out. But why does that not work here? So I want you to note something on the screen here. What's the issue?
The negative sign?
The negative sign, right? Okay. You see the fact that there's like that guy there is an issue. Okay, so this brings up a very, very important point. Attention to detail and the fact that the rules that I give you are templates. You cannot apply them unless you can take the rule and fit it on top of exactly the problem that you're looking at. If anything is out of position with the rule, you cannot apply the rule, right? And I don't know, for some reason, that's just not a huge problem why students have difficulties with math is that they don't take it seriously enough in that way. They're not as pedantic because everything else you can kind of, like you're in English class, you can say exactly the same thing tons of different ways. You can be sarcastic. You can like, yeah, everyone will know what I mean if I kind of describe it. Math is not like that. Things have to fit exactly. And you need an attention to detail, which you just can't ignore. So you can't just be like, oh, it's kind of like this. I guess there's a rule that's something like this. No, you need to know the rule exactly. And literally anything that is out of place messes up the rule. The fact that I didn't put like a letter in front of the log here means that there should be nothing in front of the log, right? Like it should be the exponential, and in the power, there's only the logarithm. There's nothing multiplying it. It's not raised to a power. There's nothing else going on. If there was something else going on, the formula would have indicated that, hey, oh yeah, you could have something here, or you can have something up here, or there will be like a variable or a letter written in the formula that says, oh, it's okay to have something here, right? But the fact that that is not written is something that you must pay attention to. That minus sign kind of messes things up. So that's an issue. There was no place for this in the rule. And so, give you a pro tip. It might seem obvious, but for whatever reason in practice, it's not. So I'm just going to tell you guys, the rules are your templates. It's not okay to kind of know them. Know them exactly. They must fit, I don't know, on top of the problem you want to apply them to. And I mean, this is important enough to not make it a side comment. Let me actually put that right up under the example, because it's actually a very common error to show up. People kind of know in the rule and they're like, oh, I know E's and LNs cancel. So whenever I see an E and LN, no matter what else is going on, I can just cancel them. That is not true. You have to obey the rules. Okay, so yeah, that would not be what you want to do. Okay, so now let's talk about what you should have done. So the answer is actually a half, but how would you actually get that? Okay, back to. So e to the minus ln2. Here's one thing you could have done. So you could have move the -1 outside. And why can you do that? Because there was a rule that's true. It's a law of exponents, which we also covered yesterday. Right? So that is doable. It fits exactly on top of a formula. This is like an X. This is like the A. That's like the B, right? Or in this case, the -1 is the B and the ln2 is the A. There's a formula that I can fit right on top of this and apply this rule, right? So now that's one thing. And now the rule inside applies because I have the E and the ln right beside it. And so inside there, I can cancel the E's and the ln. That gives you 2. You can actually like do that. And that is since a to the ln log a equals x, you can actually just like cancel the base and the log. And we learned last time, whenever you see ln, it means it's a logarithm with the base is e, right? And so now you have 2 to the -1, which is a half. And that is the correct answer. There were other ways you could have done this, or so yes, you have to be very specific. You have to be pay attention to detail, but it doesn't mean that you don't have any wiggle room. There are actually many ways to skin a cat. Oftentimes, you can do a problem several different ways. Here's another way you could have done this. Instead of applying an exponential rule first, you could apply a log rule first. You could have moved the -1 up top, right? You could actually move that up here. Because since we know that if you have something in front of a log, you can move that number up. Usually it's more convenient going from right to left, but there are times when it's convenient to go from the left to the right. And so that is important. I also want you to know, since we're here, and I'm thinking of all the mistakes that I tend to see, note, me saying this, it's not the same as this. Which another way to write that is to put the n on the log instead of the x. Okay, so the notation is actually important here. Right, there's a difference between raising an entire log to a power and raising the thing inside of the logarithm to a power. A logarithm is kind of like a function, f of x. You can skip the parentheses if you only have one thing. And so what it means is, remember how we looked at functions yesterday? It's just a placeholder, right? So there, when you put something inside here, it's inside there. So things go inside the log, not beside it. And it's very important you understand that distinction, right? There's like something inside the logarithm. The logarithm is like an f of x function, right? So when I say log x, I don't just mean log times x, because log by itself makes no sense whatsoever. It has to be operating on something, right? So just to point that out. So I can apply the log rule, and what's really going on is that the 2 to the -1 is inside the log. And now, yeah, I can cancel the e and the ln because they're right beside each other. And so I get 2 to the -1, which again is a half. So lots of ways you can do that. There are other ways you could have done this, but I think those are the two most straightforward ways. So yeah, the answer to that was a half. Okay, this one. Well, again, there are several ways you could do this. One for one, yeah, the E and the ln, they're right beside each other. So you could do that. You can cancel those and then you just get what's inside. And for two, I know that this notation, I want to, again, what I just explained, it means this, right? It doesn't mean, and that is not equal to, if I wanted the log itself cubed, there's a difference if I write the cubed in front of the E versus after the E. And this would be equal to ln of E cubed. Okay. So I'm being a stickler in explaining notation because it's actually super important. We looked at one of the mistakes yesterday, which is just not paying attention to parentheses. But that's really just a part of a much larger problem that students have with mathematics. They don't pay attention enough to how things are written and what positions things are written in. It turns out the position that the symbols are in are actually super important. And that kind of messes students up a lot. So yeah, the E is being cubed. Now there are tons of ways we can actually do this as well. We could, this cancels, right? And you get 3. Since log to the base A of A to a power is just a power. That's one way you could have done that. Here's another way. We could have started out very similarly. Get ln of E cubed. Then you could apply the rule where you just move that down. And then you get 3 because ln of E is 1, which is it's like a nice to know fact. Ln of E is 1. And in general, log to the base A of A is 1, right? You have to raise A to the power 1 to get A, right? Makes sense. So yeah, so if I have, say, log to the base 2 of 2, well, that's 1, right? So log to the base of anything of the thing is 1. So that's something that you can generally know. And remember, log of 1 is 0. So yeah, so you could get 3 that way. You could have played that game in the top, done that, and then the E and the ln cancel to get that. So you can get to the correct answer in a multitude of ways. I wouldn't, at this point, recommend one way over the other. It's just whatever you happen to see first, just do that. Here, there's not much benefit for one method over the other. There are times when I can show you several ways to do something, but I would recommend one way over the other. But when it comes to applying like log rules and doing basic computations, there's not really any benefit to it. So I wouldn't worry about seeing a particular way. Just get through the problem. Make sure it's much more important that you know what rule you're applying at any given time, and that rule fits exactly on top of the problem that you're trying to do. That's the important thing. Yeah, so we have that. So 3 was that answer, the answer to that one. Now, don't have anything to say this. Okay, so I think with a lot of these, I'm already made a bunch of detours. I don't think I'm going to need to do that much anymore. So I'm explaining a lot of concepts here, which as time goes on, I'll have to explain those less because once I say them, we know them now. We know these things. All right, so I can start doing things. I should have made this. And I'll just be extending the page. All right, cool. So this guy, again, we've already learned our lesson here, hopefully. The fact that the 5 is in front of the ln is a problem. You need to get rid of it. You can either get rid of it by moving it up onto the 2 or just moving it off to the side. Arbitrarily, I'm going to do that. That's 32. Many other ways. Right? None necessarily better than the other. Now here's a slightly interesting. Oh, let me look that. Did anyone do D? Oh, I see Jhevon answering some questions in the chat here. I didn't pay attention to when he said it, so. What is the answer for this one? Did anyone get this far? Like to take a shot at it? X squared over y? X squared over y to the 5th? Well, let's see. Lots of ways you can do this. You could do this. Since we know that something to something minus something is just that, right? That was a law of exponents. So because there's a negative in the power, I can move them down. And then I know that the 5 in front of the ln is going to cause issues, so I can move that up. And now we're in a situation where the e's and the ln's are right beside each other. So it is x squared over y to the 5th. And yeah, tons of ways you could have done this one as well. So instead of invoking a division, I could have invoked the multiplication rule. Instead of moving things up to a power, I could have left them, I could have brought the 2 down. Then I could have shifted the 2 outside, shifted the minus 5 outside, and then inside this would become x squared. Inside that would just become y to the minus 5. So again, you would get x squared over y to the 5th. Whatever way you do it, just make sure it's legal and you get the right answer at the end.
Could you scroll up to show the rule that you had before this one?
This one?
Yes.
And by the way, so yesterday's notes is going to be important as well, because that's where I went over the syllabus and I also mentioned a bunch of the rules that we're talking about now. So yeah, all those rules I'm using there were here. We did that yesterday. And the log rules we're using are here. So laws of logarithms, we did that yesterday. By the way, I posted the link to the class webpage in the chat. I don't know if anyone came in late. I'll do it again. And if you actually go to that link, there is a section in there that says lecture notes, and you can actually get linked to this page, and you'll have all the notes. Yeah, it's like an online view to what I have here. So you'll see all the tabs, and you can move through them and access the notes there. All right. Okay, this one. What's the answer?
Is it 2 to the 5th?
Yeah, you can straight up just cancel these guys. Right, you get 2 to the 5th. Or could have canceled this guy, and you would again get just 2 to the 5th. Yeah. Okay, what about F? Let me leave that for a second. Although, like I said, if you went to that class webpage, you'll have a link to the notes, so you can scroll back up of your own accord if you'd like. Yeah, so I also posted the link in the chat directly to the notes. So if I'm moving a little bit too fast for you, which is completely understandable, you'll be able to scroll back up if you want. And by the way, if I'm saying something you don't understand, it's okay to like stop me and ask me a question. I'm not talking to myself here. So we have a guess in the chat that the answer is 1/9. Let's see. So we have laws of logarithms that will allow us to combine them. And we actually know what, remember, log to the base a of b equals c is the same as saying a raised to the c equals b, right? So we saw that example. Okay, log to the base 2 of 8 was 3 because you had to raise 2 to the power 3 to get 8, right? So now when you see something like log to the base 3 of 100, you're like, well, what do I have to raise 3 to get 100? It's not, it doesn't really make, you can't really think of that number, right? It's kind of weird. However, you don't really have that. So for all of these, there are very weird numbers in the beginning. 3, what do you raise 3 to get 18? Like, who would know that? What do you raise 3 to get 50? But we do have other log rules that allow us to combine logs, right? So instead of evaluating them one by one, I'm just going to use the log rules to combine them, and hopefully we can get something out of that. So that's what I would do here. So we know log of something minus log of something else is log of the division. So I can combine the first two to get that. And now I have log of this thing minus that log, I can combine again. Which, because we're all great at algebra, we know that that's just the same as multiplying the denominator by 50. And so now we have a bunch of numbers where it's like, now we can actually start to reduce the fraction here and get something nice. So 10 goes into the 5 goes into 10 2 times. 2 goes into 18 9 times. So now we really just have log 3 of 1 over 9. Now that's a lot nicer. I know what 9 is as a power of 3. So that's what I have. But 9 is actually 3 squared. So that's what I have. And then applying the log rule, I get minus 2. Because I have log to the base 3 of 3 to the something, you just get the something by another log rule. So minus 2 is the answer. Surprising. Yeah? While I'm on the topic, because I actually taught 2 Calc 1 classes in the spring, so again, the mistakes are fresh in my mind. When I say log of x divided by y, it is not the same as log x over log y. That's not true. This is actually equal to log of x minus log of y, right? That was a log rule. So I see students all the time when they see two logs dividing each other, they kind of push it in like the thing, just one log and then of the division. That's actually incorrect. So that's not the case. Similarly, log of x times y is not the same as saying this, right? Remember, we have rules. There are rules to this thing. We know that this is actually an addition. Also, logs do not distribute across sums. What is this? Well, I didn't tell you guys because it's above our pay grade in Calc 1. So yeah, logs do not distribute across sums. So resist the urge to kind of, I can just distribute this, yeah? No, you can't. It's not legal. If it were legal, I would have told you. And that's going to be something that you can have with a reoccurring theme. See all your nice little algebra rules like, the distributive law and doing all that stuff. Whenever those things are true, it's very nice that they're true, and I'm going to tell you that they're true, right? So the fact that I didn't give you a rule that said something like that, you can kind of assume that it's not true, right? Because if it were, I would totally have pointed it out, right? Because distributive law is a super nice property, right? Whenever you can distribute something, it's super nice that you can do that. It makes your life a whole lot easier. So the fact that if I don't give you a rule that shows the distributive property is true, you should assume it's not true and don't just make up your own rules, right? You don't do anything unless you're following some rule that I gave you, and I will give you all the rules, right? So the only rules that I'm not going to explicitly state outright are a lot of rules that I would have expected you to know since algebra and pre-calc class. But other than that, I would give you every single rule that you will ever need to know to do any problem, which means that if you're doing something and I never gave you a rule for it, chances are you're wrong, right? So just to point it out, especially if it's something that's super nice and, I can just simplify it like that. That's super cool. And Jhevon never gave me that rule, but I'm going to try it anyway. the chances you're wrong is very high. Because if there's a super nice rule that lets you do everything quickly, I am going to tell you about it. I promise. Right? If I don't tell you about it, it's because it's not going to work. But yeah, students fall into this error all the time. Just like, oh yeah, I'll just distribute the log. Dude, if that were true, Jhevon would have told you about it, right? It's not true. It's not equal. They're not the same. Just to point that out. The rules are your templates. I really, really mean this. If there's not a rule that says you can do it, you cannot do it. Okay, just don't do it. Okay. All right. Again, tons of ways we can do this. Also, just recall a notational thing. If you just have log with no base on it, it really means base 10. Depending on context, yeah. This is the standard logarithm. That's why we don't say it standard log for science and engineering. Because engineers need to count on their fingers. 1, 2, 3. So, you know, we do a lot of things in base 10 because we have 10 fingers. But there are contexts in which it's not great. In other situations, standard law, it can change. So I don't know exactly what all of your majors are, but say in computer science, the standard log is base 2. Because of binary, right? Zeros and ones. If you're in math, let me say advanced math, if you see LOG, they really mean LN because no one works in a base other than E. Why would you do that? It's super nice for math. But for us, the assumption is most of you are going through science or engineering or something similar. So that's usually the standard. Okay. That being said, again, there are tons of ways you can do this one. Simplify inside here. How do I deal with log of 10,000? It's 4. Well, yeah, you can just think, what do I have to raise 10 to in order to get 10,000? It's 4, which, right, 10, 1 with 4 zeros. And so those would cancel. Oh, is that the last example? All right. Don't worry, we have tons more. Examples 2 and 3. I know what I just did. An iPad, they said. Fun, they said. All right. So there are some important skills that we need to know for logarithms, and combining them is one such skill. We actually did it in a previous example. We did it up here, right? So the logarithms were spread out, it was nicer to combine them to be able to compute stuff. So combining logarithms is going to be something that's important. So we know that when you have one log subtracting another, it really means you take the first one and then divide it by the thing in the second. So this is just log 2. And then now when they're adding, it's a multiplication. So that would be the answer, or that would be the answer. By the way, or I could have, instead of doing the rules where I combined them by doing the multiplication and division thing, I could have actually just brought all the powers down. And then we kind of do that, oh, 1 apple minus 2 apples plus 4 apples kind of thing. And you would still end up with 3 apples. But knowing how to combine logs is super important. In fact, I will tell you when it would tend to be important. Combining for algebraic tasks. Like simplifying or solving equations. So if your goal is to like simplify something or solve an equation, then chances are if you have a bunch of logs spread out, it's not advantageous. You want to combine them. You want to make them smaller. And that's going to be very useful. It turns out the opposite skill is also useful, but for a different reason. Being able to expand a log. So you have one log of a whole bunch of stuff, and you kind of want to spread them out into multiple logs. And there's a situation where that is convenient. So we need to know how to do that. Let me just here for a minute. So knowing how to combine logs, very important. It tends to be important in context of algebra and simplification and solving equations, just the basic stuff, non-calculus stuff that you would have done before a calculus class. Chances are combining your logs will help you with those things. But we also need to know how to expand them. So what I would probably do here is write that as a power. Why? Because I have rule that tells me how to deal with powers. It fits in my template. I didn't give you a template where there was a radical sign in it. So because of that reason, I'm going to rewrite the radical sign as a power. Now, what you can do with that is bring that power down. All right. So now remember we're expanding. We want to get this thing as spread out as possible. And we have log of a division. we know what that means in terms of log rules. We can make it into a subtraction. So yeah. So we have that. Is that right? Everyone with me so far?
Does the 1/2 have to go on both terms?
It does. So what I am forgetting here are parentheses. We spoke about yesterday. Don't forget your parentheses. The 1/2 should be distributed to both. And if you don't have your parentheses, you'll likely forget that. But for the time being, because I don't want to keep writing 1/2 over and over, I'm going to leave it outside. But just know that it should be attached to both. For this one, I know there's a multiplication here. And I know log of something times something is just the log of one plus log of the other. So this will be ln of x plus ln of x plus 2 cubed. Right? So are we good? I'm just applying the log rule. We're not good. just so you know, just to end the suspense. There's something wrong here. What's wrong? What's wrong with what I wrote down?
Parentheses again?
Parentheses, it's literally the exact same mistake of last time. Because the half had to be distributed, the minus sign also has to be distributed. Need parentheses here. Negative, it should be minus ln x minus that. So that's what we have. Because the idea is to like write things in very simple terms, I'm going to move that 3 down, make it a little nicer. Yeah, by the way, this I think is a good spot. With practice, you should be able to jump here in one line. Now, I'd rather, generally, I want you to write stuff out so that I could give you partial credit. But to be honest, if you skipped the first 3 steps that I did and just jumped here, I would be okay with it. Like, if you work enough with logs, you'll realize that you should be able to like expand it in your mind very quickly. So you see the division and you see the multiplication in the denominator, you're going to know, oh, it's log of the top minus log of the one term minus log of the other term. With practice, you'll kind of see, oh, it's going to be this, but plus that, minus that, plus that. And so a lot of students can go directly from a situation where there's all this multiplication division to like the spread out version. And I think it's not too much of a stretch to say you could literally jump from the line at the top of this page to that line I just indicated with one step. And you'll see that with a lot of practice. But because it's a new thing that we introduced yesterday, I just slowly walk through the steps. Yeah, so now we're here. And we can actually take this further. This can be simplified a little bit more. And maybe it's the log of x squared minus 1 that has a power. Nothing else has a power. You know, it's kind of like the sore thumb. So we can just you know, do this. Right? Reagan is shaking her head. No, you're trying to catch me, John. Yeah, I know. Nah. Yeah, that is no, you cannot do that. It's very illegal. I just explained that earlier, by the way. You cannot distribute logs across sums. So that's not okay. But there is something that could be done. Do you see anything?
You could expand the difference of perfect cubes or squares.
Difference of squares, right. So, well, not expand, the opposite. You can factor it.
Yes, factor.
And so that can be broken down further into ln of x minus 1 plus ln of x plus 1. And I think that's a good place to stop. Actually. So we started here, nice compact logarithm, and we ended up here, which is actually a nice thing to do. Expanding logarithms. So this doesn't apply. It's not really an algebra thing, right? If your goal is not to simplify or solve an equation, but you actually want to do some calculus, like I haven't told you the rules yet, but when I do, you want to apply expanding logs would be more beneficial than actually leaving them compact, right? So if you want to do algebra stuff, combine your logs. You want to do calculus stuff, expand your logs. There's a reason when you would do one versus the other. So there are times when I can ask you to do some sort of calculus procedure on this, like, oh, differentiate this. And it is significantly easier, like not a little bit easier. It's a huge amount easier to do it on this guy than it is on the first guy, like by a lot. And I often get students who get in trouble because of that. So I would put something like this on a calculus exam, like, oh, differentiate this. And they were like, man, Jhevon, I spent like 10 minutes on that problem because it was like I had to do chain rule and quotient rule and do this and put it this inside of that. And I got this huge fraction in there. Dude, you can get to this line in one step. And then the calculus is on this. And then the calculus on this is another step. It's like a 3-step problem and you're done. Whereas if you were to do it on the contracted form, it's like, it's really crazy. We'll see it later. But just so you know. So yeah, you want to do calculus, expand your logarithms. Because it's much, much easier. Okay, so yeah. Let's solve a bunch of equations. I'm not going to need that much space for that one, I don't think. All right. So in one sense, there is like zero work that you have to do for this. You can literally just be like, all right, x equals ln of 12. And that is since, and that would be your answer. And that is since we have a rule that says log to the base a of b equals c, means they can take a raised to the c equals b. So in other words, if I have ln of b equals c, it's the same as saying, remember, the base is e. So it would be the same as saying e to the c would equal to b. And so obviously you can go the other way. So e to the c equals b means that your c must be ln of b by just turning the rule around. That is correct. And I think conceptually it's just a lot of steps to go in your head personally. So there's another way I want to show you guys to do this, which highlights a very important technique. It's still not going to be much longer, but I just want to show you. So we remember we had that rule that exponentials and logs are inverses of each other. So you can use one to cancel the other one out. And so that's what we can do here. We can actually, if e to the x is equal to 12, then I'll get the same answer if I plug both of them in the log function because they're equal. So what I can do is I can take an ln and throw them inside, both of them inside of an ln. Now this procedure, I will informally refer to it as log both sides. Right? So I can have an equation like this and I'll say, oh, just log both sides. And I really mean this that I just did. And so that's informally. Right? So you log both sides. And now what you can do is you can now apply the rule, that those guys cancel. And so you just get x. Then you have ln of 12 on the other side. Right? Conceptually, I think it's easier to just think of it as doing that operation, kind of like moving things on the other side of an equal sign. Oh, I see a +2, I -2, because minus is the inverse operation of plus. Similarly, if I have an exponential and I want to get rid of it, I can log it because log is the inverse of the exponential. So yeah, you can get to that by logging both sides. So in the next example, it's actually very similar. So you see this, e to the 2x minus 7 equals 10. And sometimes I just kind of write the ln in here. It's like literally write it over the problem. And that is me logging both sides. Why? I want to solve for x and it's stuck inside of an exponential. How do I get something unstuck from an exponential? Use a logarithm. So You do that, these guys would immediately cancel. So you just get 2x minus 7 on this side and ln of 10 on that side. And so you can add 7 to both sides and then divide both sides by 2. And that's your answer. Note, another mistake I see all the time. If you have log of something and it's divided by something else, you cannot cancel that thing. Like it's not the same as that. Right, so I see students do that all the time. So they'll see something like ln of 18 divided by 2, and then they'll be like, oh, I can cancel the 2 into the 18, right? And just get like ln of 9. No, you cannot. That's wrong. Don't do that. Right? There's no rule that says I can just take something and cancel it inside of a log. If there were, I would have told you about it. So some people might be tempted to see, oh, they see the 2 and the 10 here, and they'll cancel it. First of all, you're canceling across a sum, which is already illegal. But some people might split it off and have a 7 over 2 plus the ln of 10 over 2, and they're like, oh, that's ln of 5. It's not ln of 5. There's no rule that says I can do that. So that's the answer. You have to write it like that. Here's another one. Again, you can sort of just do this as a one-liner. So you can say, well, this would mean that x is equal to e to the 7. Since, again, that rule, I know that ln of some x equals y is true if and only if e to the y equals x. We saw that yesterday. But again, there's another way to think about it that I think conceptually is easier. Is you can use an appropriate base to kill a logarithm. In other words, you put them in an exponential. So I would plug both of these guys into the exponential function. Right? So again, let's say this as, this is very informal because it actually doesn't even make any sense. English-wise, I might say e both sides, which is totally not what I'm doing. That doesn't make any sense to say that, but I might just say that. Or, you know, it's exponentiate both sides or something like that. And it's very informal because it's linguistically incorrect. But it just kind of reinforces the idea that if you want to get rid of a logarithm, you can use an exponential. Which exponential? The best one to use is the base of the logarithm. So ln means base e, so I'll use a base e exponential. And why would I do that? Well, now these guys would cancel. Right? So I see ln of x equals 7 as it's given here. Sometimes I'll literally just write this on the problem and cancel in one step. Yeah. Okay. What do we do here? I think I have internet. Is my OneNote offline? What do we do here?
I would start with taking the natural log of both sides.
Okay. Then what?
I would maybe not. I would expand the ln 5e to the 3x to ln 5 plus ln e3x.
Mhm.
And then use your log rule to bring the 3x out front of the ln term that it's on.
Yeah, and you can even just cancel that straight away. Yeah.
Yeah.
So we have ln 3 equals ln 5 plus 3x. Move the ln 5 to the other side, divide both sides by 3. You could get that. Or you can get that your x is ln of 3/5. Here's a slightly nicer way. That is actually correct, but I can tell you from experience, there are a lot of students who would go from this line and not get to that line. They'd mess that up. They would do something like cancel the ln and the e right away, and they would get 5 times 3x or something because they're not paying attention to the rules. So I'm glad that you did that, but for the average student, I think it's kind of risky doing it this way. So what I would actually do is before you log both sides, because you know that you need the log right beside the exponential, you'd want to isolate the exponential first. So it's probably a good idea to first divide both sides by 5. Right? And then you can like log both sides. So that would give you ln of 3/5. And then that would cancel right away to get 3x. And then your x is ln of 3/5 all over 3. Right? Just so you wouldn't have to like expand stuff and get a little bit crazy. So it is correct, but it's not wrong, but it's kind of risky from a student perspective. There are times when I'd make weird recommendations like that, where I would say, do it this way instead of that way. And the reason why I say that sometimes it's just because statistically speaking, most of the time when I see students take this route, they end up messing it up somewhere versus if they happen to choose this route, they end up getting it right. So yeah, there are times when I would recommend certain things like that. So I think this is a slightly nicer way, even though they're both correct. And it does take up less space, which is also nice. If you have two methods and one tends to get the problem done quicker, I would probably want to do the quicker way because the longer you're writing, the more opportunity there is for a mistake to happen. So it's just like a strategic thing. So you see this, of course, what I would try to do is put log both sides base 2. And so now my x is going to be plus or minus the square root. And that's that. Yeah. And you can actually plug that in. So if you have like a 2 raised to the plus or minus square root, log base 2 of 5 minus 1 squared plus 1, you would get the square would kill the negative sign, so whether it's plus or minus, and it would also kill the square root. So you'd get 2 to the log base 2 of 5 minus 1 plus 1. That you can write it as 2 to the log base 2 of 5 times 2 to the minus 1 plus 1. And so square root of log base minus 1. And then you would just get x squared plus 1. Oh, sorry, that plus 1 was in the power. That's why. Okay. See, when you write things in the wrong position, that plus 1 is supposed to be up here. So those guys would cancel right away. And you just end up with that, which is 5, which is what you should have gotten. Also, you may worry about whether this is defined as a real number. Right, because we know we can't take the square roots of negatives and get a real number, and we don't deal with complex numbers in this class. But it's okay. Because we know that logs increase. So I know that, for example, log to the base 2 of 4 would be less than log to the base 2 of 5. And I know that log to the base 2 of 4 is 2. So this means that log to the base 2 of 5 is bigger than 2. And so my log to the base 2 of 5 minus 1 is actually bigger than 2 minus 1, which is 1. So it's definitely positive. So it's not an issue. And we know that logs work like that because they get bigger over time. So the log 4 is definitely going to be below in terms of y values than a log 5. So the bigger the thing you're logging, the bigger the overall answer is. Logs increase over time. They're an increasing function. We'll talk more about what that means, actually. How many more of this? How do I give some examples? I'm laughing in my myself in my head. Like you can never please everyone, right? You're always going to have students who believe you didn't give enough examples, and then you're going to have students like, you gave too many examples. You're never going to get it just right, so I'm not going to worry about it too much. Like someone's going to complain at some point about, hey, yeah, it's going to happen. So I'm not going to worry about it. This one. How do we solve that? How many more do I actually have? Ugh. Yeah, I think we learned our lessons here, so I'll go through those relatively quickly. What about this one? And then we'll take a break. Ideas? Log both sides. But you can't really log both sides because you can't take the log of 0. We learned that yesterday. Move the 6 to the other side and log both sides. Wouldn't really help. You'd have a log of a subtraction of exponentials. Can't really do anything with that. What do we do?
Do we treat it like a quadratic and then you factor it?
Exactly. It is a quadratic in hiding. Gasp. It's a quadratic equation. In e to the x. So it's kind of like if you set y equals e to the x, we have, I don't know, why did I say like? Let's cancel. Here. So if you were to say y equals e to the x, you'll realize what you have is y squared minus y minus 6 equals 0. And if you saw something like that, you should know how to deal with it. You'd factor. 3 and 2 would work. Minus 3 plus 2. And so you'd get your y would equal to 3 or your y would equal to minus 2. So it's essentially the same strategy here. The fact that it's an e to the x instead of a y is completely irrelevant. It fits a template of a quadratic equation, and we know what to do with that template. So this is going to factor into e to the x minus 3 times e to the x plus 2. So this gives you e to the x minus 3 equals 0, or e to the x plus 2 equals 0. So this means that e to the x equals 3, or e to the x equals minus 2. So here we know we can log both sides. So x equals ln 3. Or what about here? Can I log both sides? Yeah. Yeah, so no. Just checking if you guys are awake. That is illegal. We know that logs, you cannot log something that's negative. It's not a real number. So here you have no solution. For a bunch of reasons. One, can't take the log of a negative. And two, y equals e to the x is never negative, right? So you can, we saw the graph of that, looks like this. It never actually is below the x-axis. So there are a couple ways you can see that that would not be an answer. Getting through these, as I mentioned, you want to solve an equation or do something algebra related. You see a bunch of logs spread out. Combining the logs is going to be what you want to do. So I would get the logs on the same side. There's a log rule that says I can multiply that. Then can e both sides. Then I would get 2x squared plus x equals 2. E to the. Okay, how do I solve for x here? Do that because it's another quadratic. It's funny how those guys sneak up on you. It's not the kind that you'd know how to factor though, because e squared is a very weird number, but we have something called the quadratic formula. So it's minus b plus or minus the square root of b squared minus 4 times a times c. All over 2a. So this is going to be so what's under the radical is definitely positive, so don't have to worry about that. But will the negative be affecting things? Oh yeah. Since ln of x would be undefined. So your x only has the positive one. This last one, jeez. Again, solving an equation, I'm going to combine the logs. Here is both sides of the 10. So that gives me x times x minus 3 equals 10 to the 1. Another quadratic. I think this one factors 5 and 2 maybe. Minus 5 plus 2. Check, does that work? No. Reject. Since minus 2 is undefined. Does this check out? Log of 5 plus log of 5 minus 3. Well, that'd be log of 5 plus log of 2. That's log of 10, which is 1. So yeah, that checks out. That's that full one. And bring all the logs to one side because I want to combine them into one big log. So it's going to be 3 times x plus 2 divided by 5 times 2x minus 3. And raise both sides to the 4. So that would give me 7x on this side and 6 plus 15 on that side. Equals 3. And you can check that, but I want us to pause here. We hit the 90-minute mark, so we got to be careful. It's very hard to pay attention in math class for more than an hour and a half. So you guys even started slowing down with responses. So we're going to take a break. About 8 minutes too late, but yeah, we're done with some background stuff because knowing how to deal with logs and exponentials is going to be important coming up. But we're actually going to start calculus after the break. So let me stop the recording.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, we're back. All right, so with that little excursion into exponentials and logarithms and doing computations with them out of the way, we can finally start talking about calculus. So let us do that. Now, let's get into calculus. Let's start with the simplest question we can ask. What is calculus? In the sense, what is it? What are we studying when we study calculus? Does anyone know? What is calculus? Why are we all here? If I were to ask you, what is calculus the study of, what would you say?
Slopes of curves.
Slopes of curves, okay. What else? That is something that we're going to look at. So, basically, it is the study of mainly two mathematical objects, derivatives, integrals, and their applications. So that's mainly what, if you were to say in a phrase, like, what are we studying when we study calculus? We're studying things called derivatives, we're studying things called integrals, and we're studying how we can apply them to stuff. So now you might be wondering, well, what's a derivative and integral? So what that really means is that it branches off into two, has two branches. So calculus is the study of these things, but it's split into two parts. You have what's called differential calculus. So that's one branch. And this is the branch that studies the derivative. So studies the derivative and its applications. And most of the time in Calc 1, this is what we do. This is most of Calc 1. We're going to be studying something called the derivative and its applications. And what is the derivative? Well, that's a little bit harder to answer, at least with what we know now. So at this point, I would just say it is let's call it sophisticated. Solution to something called the rate problem. Okay, so there is a problem in mathematics called the rate problem, and the derivative is one solution to this problem. It's the most comprehensive and sophisticated solution to this problem, actually. So what is the rate problem? It's essentially this is the problem of finding what we call rates of change. We want to answer questions like, how fast is that moving? Right? So that's a very important question, and it's kind of vague if you think about it. So there's something called the rate problem, which is basically how fast is something changing, right? So how fast is that thing changing? How fast is that thing changing? How fast is that thing over there moving, right? Can we come up with a mathematical way to answer that question? Which is like where do you even begin, right? In fact, the guy who's usually thought of as the father of calculus, which is not technically correct, but we'll get a little bit more into that, is Isaac Newton. And pretty much he developed the calculus that he developed, which is what we study partially, because he wanted to figure out the motion of the planets, right? So he wanted to figure out how fast will Jupiter be in this position, right? So someone asked him a question about the solar system, and he pretty much went home and invented calculus to answer the question, right? That's how he spent his summer. What we're learning, he invented over like a few. All right, so that is the question. How fast is something moving? How fast is something changing? It's a very, very important question because, as you might have noticed in life, things change like all the time, right? Tides come in, tides come out, the sun rises, it sets, plants grow, they die, stars shoot across the heavens. Like there are a lot of moving things. And the more we are able to answer how quickly something is moving, the better we can predict and plan for stuff. So we can say, oh, the tide is rising. How fast is it rising? How much time do I have to, tie my boat to the dock or whatever, right? So it's a very important question, finding out how fast things move, how fast they change. This is called the rate problem. The derivative is a solution, the mathematical answer to what this is. And most of our time is going to be spent on that, right? So it's figuring out how fast stuff moves. And we're going to develop something called a derivative to do that. And the study of that object, the study of derivatives, is called differential calculus. But that's only one branch of calculus. There is a whole other branch. And that branch is called integral calculus. Okay. So like how differential calculus is the study of derivatives, this is the branch that studies the other guy that I mentioned up here, integrals. So this is the study of integrals. And their applications. In Calc 1, we'll introduce them, but not spend a lot of time on them. So that's pretty much what Calc 2 is about, learning more about integration and stuff you can do with it. And then Calc 3 is about kind of relearning everything, except now you're in 3 dimensions or higher. So now we are going to be doing what's called single variable calculus. So we're imagining that the universe is 2-dimensional, and we're going to do calculus in that sense. So that is what integral calculus is about. And what is that, right? So we know what the derivative is, right? But what is the integral? Well, it's another answer to something. It's another problem. It's called the area problem. Right? So derivatives solve what's called the rate problem. Integrals solve what's called the area problem. And what is the area problem? Well, this is essentially how much space does something take up? So that's the question that we want to answer. Like, how much space does this thing take up in terms of something like area, volume, etc. Which is also an important question, right? Finding the areas of things. Now, you have done geometry in high school, so you probably realize that, oh, we actually know how to find a bunch of areas of things. I know how to find areas of rectangles, circles, triangles. Yeah, what's the area of that? Right? Now it's a little bit more complicated, like this random blob. There are times when we need to know how much space something takes up, some random blob, right? Now, there is actually a nice brute force, I don't know if I would say nice, but there's a brute force solution to this. Pretty much what you can do is you can slice an object up into smaller shapes that you do know how to find the area of, and then you just add up all the areas. And of course, it's not going to be the exact area. So what you can do is you can slice it up into smaller chunks of the same thing, and just, add those up to get a better and better answer, right? So you can approximate the area very well by doing just that. And approximating stuff is fine. I know a lot of people believe that math is about finding the exact answer. We need to find the truth is, in real life, many times, even when you can find the exact answer, you don't even need it and you can't even use it. So if I'm doing a calculations, I'm like, okay, to build this thing, I need a piece of board that's pi units long. Great, good luck cutting a piece of board exactly pi units long. It's an infinite decimal that no one knows. No one has ever written this number down, right? You tell a machine to cut something pi units long, it's going to approximate pi. It's going to cut it off at a certain number of decimal places and it's going to do that. You can't actually experience pi in the real world. It's just like a mathematical thing that we know as a limiting process. So approximations are okay. So we kind of know how to solve this problem already, but we're going to give it a sophisticated solution, right? Something where we don't have to pay some guy to slice stuff up and just count all day, right? Imagine if that was a job, right? Just like this guy, oh, I count rectangles for a little. Yeah, no. We want a nicer answer where we don't really need that much brute force or manpower. So that's the area problem. And that's also an important problem to be able to solve, because a lot of things in life, we need to know how much space it takes up, and a lot of things require that we know how much space. So for example, say property taxes, you're charging taxes based on how much property you own. So, the tax man comes and like, oh, here's what you owe for property taxes. And you're like, how do you know how much land I own? Like, my land has this weird shape, right? So, you can say you're overcharging me for taxes because I don't have this. And like, how would you be able to solve that dispute, right? How would you know to stay quiet if they're undercharging? I'm kidding, don't evade taxes. But you need to know how much space something takes up, and sometimes random things like you don't have a formula for. How do you go about figuring out how much space it takes up? So calculus is about that, the study of derivatives and integrals and their applications. The derivative is really a way of us figuring out how fast things change. The integral is a way of us figuring out how much space something takes up. So calculus is really the study of those two things. Can we figure out how fast something's moving and how much space something else would take up? Now, it turns out that these two problems are actually connected. I did that to change the color. Turns out that these guys are connected. These two fields of math are connected by a theorem we call the fundamental theorem of calculus. Okay, right. Now we will be talking about this guy eventually, more towards the end of the semester, which is like 3 weeks from now or something. So we are going to talk about this theorem called the fundamental theorem of calculus, which I would abbreviate FTC. And it's pretty much a theorem that says these two problems might seem completely different, like they have nothing to do with each other. Like this guy's figuring out how fast is that horse running. This guy's trying to figure out how much he owns on property taxes. It turns out you guys are actually working on the same problem, just from the other direction. It turns out that these two problems are kind of inverse problems of each other. And you can actually figure out stuff in one realm by figuring out stuff in the other realm. And which is very surprising that these two are actually connected. Solving these problems are two sides of the same coins. Turns out that integrals and derivatives have a relationship between them. And that is specifically described by this theorem called the fundamental theorem of calculus. So eventually we're going to get to a theorem that's called the fundamental theorem of calculus. I'm going to tell you the theorem. It's probably not going to look very special. You're like, why is this guy fundamental? But the truth is, it actually branched two areas of math that were thought to be very different, very separate. Turns out they're not very separate at all. And so this is why we have calculus class, because we figured out, hey, these two things are actually together and we can group all this under one mathematical umbrella that is called calculus. And it's a super useful thing to know about. And so that's why we do it. And two guys developed the kind of calculus that we will be studying, Isaac Newton and Gottfried Leibniz. And yeah, we'll talk about that a little bit more. But yeah, that is what we're doing here, why it's important. And yeah, so just want you guys to know what the point of all this is. But most of our time is going to be spent on differential calculus. So we're going to learn about something called the derivative and how to apply it to stuff. What happened? I actually do need that. So I'll do that. So yeah, so that's what we're studying. And it turns out answering these two questions they give us a lot of benefits just for free. So you might just set out to figure out, oh, how fast something is moving and how much space something takes up. But it turns out that being able to answer those questions, we now know how to answer questions about other stuff too, that is not directly related to that. So that's kind of cool that you can get that. So where does it begin? And the answer is with limits. Know your limits, right? Now, I told you what calculus is, the study of derivatives, integrals, and their applications. So that's like a whole mouthful right there. However, if someone were to ask you, okay, give me the shortest thing, like give me like a very short phrase or like one word of what calculus is studying, the answer would be limits, right? And this is essentially what calculus is about. In one word, because it turns out the derivative and the integral are special kinds of limits. How we're going to define these objects, we're going to actually define them as limits. And so it all boils down to a singular concept. The fact that these two are connected kind of tells you that they kind of come from the same thing. So it turns out they all branch out of this study of something called limits. And so that's where we're going to start. We're going to start studying limits. And let me, instead of moving this on the iPad, move it over here. Ah, there we go. So we're going to start with limits. So yeah, that's why we're all here. Now let's actually get into it. Limits. Now, we will see the specific maybe I should use the word precise. Definition of what a limit is soon. But we start with a more intuitive definition. For what a limit is. So here's how I want you to think about it the majority of the time. And we're going to see a very mathematical way to think about it, even more mathematical than it's already going to be. But this is kind of a fuzzy definition, but it's very usable and very workable. So here is how we're going to define it. We say the limit as x approaches a of f of x is L, right? So this is a phrase you can say. The limit as x approaches a of f of x is L, right? Someone can say that phrase and write this symbol, limit as x approaches a of f of x is L. To mean the following. So I'm going to describe the limit as an idea, right? The intuitive idea. To mean as x gets close to a, the output f of x gets close to L, right? So as the x value gets close to the number a, the y value is going to get close to the number L. That's pretty much what it is. When your input is getting close to something and then you're watching what the output gets close to in response to that, you say you're taking a limit, right? You're finding the limit as x approaches a of this function. And pretty much what you're doing is you're pretty much watching the y value. How does the y value respond when my x value behaves like this? I.e., as x gets closer to some value a, we want to know what the y value is getting close to. If anything. And we want, and you'll see this come up later, to be unambiguous. So what is the y value getting close to is what we want to be able to answer. And we want to answer that unambiguously, right? Meaning that everyone else should be able to work out the problem and get the same answer that you're getting. Everyone will agree. There's no ambiguity. You don't have to debate with anybody. You can't say, well, maybe it's this, and someone else can have an argument why it's that. No, there's no argument. This is the answer, right? Because it's already kind of fuzzy. You don't want it to be extra fuzzy. So, and it's fuzzy because of this word here, close. It turns out that that actually makes the definition vague, and why it's too vague to be an actual definition, more of an intuitive one, because what does close mean, right? Close will be different to different people, you know? There's some people, you know, they're talking to you and they're right here, and like, give me some space, man, you're too close. And it's like, he doesn't think you are close. Like, he's like, well, that's how I talk to people, right? But for you, it's close, for him, it's not, right? So getting close to something is something that, depending on who is measuring, they might say it's close if it's 1 centimeter away. Nah, 1 foot away is close enough. Like, how do you, that's kind of vague, but we want it to mean something specific, and that's what we're going to get to. And by close here, we mean arbitrarily close. And essentially what that means is, i.e., as close as you want to get. And so that's why we need unambiguous answer. We want to have an answer that no matter who's looking at the problem, they'd be able to say, yeah, that's close. I think that's close, right? We want to take out the vagueness of the word close. And that's where the specific definition is going to come in. We're going to tell you exactly what close means mathematically. If this definition is fulfilled, everyone would agree that you're close, regardless of how they think about closeness in real life. And so that's what the limit is about. So it's very important that you understand limits are about getting close to things and not actually being at the thing, right? You're worried about getting close to something, not necessarily being in the position of that thing. And that's going to be fleshed out a little bit more. And so we can say this phrase, the limit as x gets close, the limit as x approaches a of f of x equals L, to mean when my x gets super close to the value a, my y value is going to get super close to the value L, and everyone would agree with me that that's the value, right? That is the concept of a limit. What is the y value getting close to when x gets close to something? So, to take a limit or compute a limit, or you can say evaluate a limit, we are answering what is the y value getting close to. And it's implied as x gets close to something. Okay, now that's the intuition I want you to get. When we're studying limits, you're studying what's the y value doing? Is it getting close to some particular number? Can I identify that number? And would everyone agree with me that that's the number? Right? It's essentially, right? So it's very vague. Let's actually do some examples. And I do have some examples over here. So we're going to illustrate this idea with some examples. which, like a cooking show, I conveniently prepared stuff ahead of time. But yeah, you throw this in the oven and ding. It's like, no, what happened? Like it didn't look like that when you, okay. Maybe it's just me, but I think like these cooking shows are like, it did not look like that when you put it in the oven. Some trickery afoot. Okay, so let's see what I actually mean by this idea of getting close. Okay. So evaluate the following limit. Right? So this is read as the limit as x approaches 2 of 3x minus 1, right? So I want you to evaluate that. What is the limit as x approaches 2 of 3x minus 1? And I'm going to sort of slowly lead into this so you can get the idea of what we're doing. So 3x minus 1, if I was to set that equal to a y value, y equals 3x minus 1, I know what that is. That is just, that's a straight line, right? So and in fact, I know that it goes through minus 1 with positive slope, slope 3. Right? So this is y equals 3x minus 1. Now, at some point, there is a 2 here. And I want to know, as my x gets close to the value 2, what is my y value getting close to? Right? So that's the idea. So now it's like, all right, let's say I'm getting close to 2 over here, right? So now what I care about, I don't care about that. I actually care about the corresponding y values that these guys would give me, right? So I'm really tracking what's going on over here, right? So as my x gets close to 2, it means I'm on the function and I'm moving closer and closer to something, and I want to know what that something is. From the other side, though, I can say, all right, I can get close. What if my x value is getting close to 2 from over here? Then it means I'm on the graph moving down to there, which means if I'm tracking along the y values, it's moving down to here. Now, there's going to come a point where we can get to a value that everyone's going to agree that that's the value, right? So what is the value? Like what would we get close to? If my x is getting close to 2, what is going to be the, what would the y value get close to?
Would it be 4?
Y4? Why do you see 4?
I don't know. I just thought maybe like you plugged in 2 for x. But
Okay. And what would you get?
oh, I'm sorry. 5.
5, right? You'd get 5.
My bad.
Right. So 5 would be here, right? And really, everyone in the world would agree with you that that's the answer. Like, no one's going to say, no, it's 7. Like, no, you're not getting close to 7. You're getting close to 5. But you just said something very important. Well, I could just plug in the 2. So it's like, why are we worrying about getting close to the 2? I can literally just be at 2, plug in the 2, I'll see the y value, right? So it turns out as x gets close to 2, y gets close to 5. So another way of saying that is the limit as x approaches 2 of 3x minus 1 is 5. the y value would get close to when my x value gets close to 2 in the expression 3x minus 1 is 5. Everyone would agree with me on that. When x gets close to 2, the expression 3x minus 1 gets close to 5. There's no escaping that, right? And that's going to be, that's the answer. Now, you may see that we could just plug in 2. And be at 2, right? And so, like, why are we worried about getting close? We could literally be there. You can't get closer than actually being there, right? And so you would get your y equals 3 times 2 minus 1 equals 5. But that's not the idea behind a limit. It's not, it's very different from plugging in. Now, there are times you can plug in and get the answer. Taking a limit is different from plugging in. And to illustrate that, let me give you another example. Let's look at this one. Very similar question. I am asking, what is the limit as x gets close to 2 of x squared minus 4 over x minus 2? Now, if you came from pre-calc, you know about pre-calc, you would say, but I can't actually plug in x equals 2. That would make me divide by 0, and that is going to be illegal. Jhevon went on a whole rant yesterday about you can't divide by 0, and it's like, yeah, so I can't plug in 2, so that means the limit, it's not going to work. It's undefined, right? And so that's what you might think, right? It turns out that that is actually not the case. In this particular example, it turns out that the limit does actually exist, and you can actually find a meaningful answer that literally everyone would agree with. And this kind of shows you that the limit actually is different from plugging in, right? So so how would we actually do that? So let's actually look at let's do the same kind of strategy. Let's actually draw the picture and kind of see, can we figure out what's going on? So the important thing is that we cannot actually be at 2. The same trick that worked last time, not going to work now. I would divide by 0. So let's actually play the same game. Okay, so what does this graph look like? So here's something you can realize. Over here for a bit. So let's say we have y equals x squared minus 4 over x minus 2. We can't be at 2, but otherwise, This is just a fraction, right? You're going to plug in a number for x. You're going to, and you can say, oh, it's this number divided by that number. It's some sort of fraction, right? And so that means idea, light bulb, we can reduce it. So what you would do is, all right, so I have x squared minus 4 over x minus 2. And I know that x cannot be 2. So what I can do is I can factor that's going to cancel. And I would get this guy as long as my x is not equal to 2. Now this guy, we do understand. That's another straight line. In fact, the y-intercept is 2, and it has positive slope, but we can't actually be at 2. So you're going to notice that if we're at 2, something is going to be off. So at 2, there's kind of a hole here. You can't actually be at 2. But other than that, if you're not at 2, it's just a fraction. I can treat it like any other fraction. I can reduce it, and it reduces to this number, right? The output of this and the output of that will be the same all the time, every time, except at the value 2. So this is our picture. And now we're going to play the same game, right? We're getting close to 2, which means I'm on my graph doing that, which means my y values are correspondingly moving up towards something. And I can get close to 2, which means I'm on the right side of this function doing that, and my corresponding y values are doing this. So they're moving towards something. What is that? What are they moving towards? Minus 2. What's the y value getting close to here? Any guesses? So we just said that this is the same as x plus 2, as long as we're not at the value 2. So that function behaves exactly like x plus 2, except for the point where x is 2. What is the value we're approaching here?
Is it 4?
It would seem to get closer to 4, right? If I could have been at 2, that would have been a 4, because I would just be able to plug in the 2 here like I did last time, right? So here, as x gets close to 2, our y gets close to 4. And in this case, it's literally you have to get close because you can't actually be at 2. Being at 2 means division by 0, and we know what happens then, right? So I would be able to say the limit as x approaches 2 of x squared minus 4 over x minus 2 is 4. So the function is undefined, but the limit is defined, right? So even though the function is not defined, we can't plug in 2. The limit is defined, right? So the limit does exist. Right? And that kind of shows you that taking a limit and plugging in a number they're different, right? So they're not the same thing. And so you just have to be careful of thinking they're the same thing because they're not. So it turns out that the limit does exist, right? So there is actually an answer when you put a limit in front of something, right? By itself, x squared minus 2, x squared minus 4 over x minus 2 is meaningless at x equals 2. But I put a limit in front of it. Hey, now we have an answer. It's 4, right? It's not the same as plugging in the 2 because we're not allowed to plug in the 2. So that's very important. Okay. Here's a third example. So I'm doing these examples, and I'm not going to expect you to draw a picture every time I do a limit, but I really want you guys to get the concept of what we're doing here, because that will actually help you out in certain situations. So eventually I'm going to teach you how to compute limits where you don't have to draw a picture. You can actually do calculations and figure it out. But until then, I want to make sure that you understand what it is that I'm doing. You're not exactly plugging in, even though there are some situations in which it might seem like that's what you're doing, but you're not. I want you to get that. The limit does not care about being at the point. It only cares about getting close to the point. And that's the point. Okay, let's get, yeah, that's too much alliteration there. Here's another one. I just defined a function that is a piecewise function. And we all know what that means since we're all geniuses at pre-calculus and algebra. So let's actually figure out what that would look like. In case we want to play the same game. All right, so we know a piecewise function, what that means. It's defined for, it's potentially defined differently for different values of x. And so this one is one thing if our input is less than or equal to 2, and it's another thing if our input is greater than 2. So there is like a space cut off here at 2, where the graph could be one thing on one side and another thing on the other side. So on the left side is when we can be this quadratic, x minus 2 squared. So that's a quadratic. At 2, if x is equal to 2, that output is 0. So it's going to be like this. And then it's going to move, it's like a parabola. So it's going to be like, right? It's going to be like that. Right, and I can know that this is going to be 4. Right, so on the right side, it's a parabola. On the left side, it's a parabola. So this is y equals x. Y equals x minus 2 squared. All right. Now on the right side, it's something different. It's 3x plus 1. So I know what 3x plus 1 looks like. It's just like a straight line. It would have the y-intercept going through plus 1 with positive slope. But that only works on the right side of this line. Now at 2, 3x plus 1 would be like 7. Now I cannot be at 2, so I draw a hole. And that is at 7. And on the right side is just a straight line with positive slope, so it's moving up like that. So that's the picture, right? So all right, let's play our same game. Let's figure out what is the limit as x approaches 2. So let's get close to 2 like we've been doing. So all right, so as I get close to 2 over here, then that means I'm on my function coming down like that. Corresponding y values are going down like that. They're heading towards something, right? And you might, of course, recognize at this point our y equals 0. But someone else could fit. Well, you know, I got close to 2 over here, which means I'm on the right side of this function coming down like that, which means I have corresponding y values moving down like this, which means I end up here. So of course my y equals 7 here. So now the question is it 0 or is it 7, right? So what do you guys think? Is the answer 0 or is it 7? Well, I guess some people are like 7 is a lucky number. So now you have like this thing where, you know, people are like, they're like fighting each other. I think the answer is 0. No, I think the answer is 7. And then like, we're all like, but you see, the fact that there is even such a discussion is a problem. So back above here, I said, should be unambiguous. You shouldn't be able to have an argument over which number it should be, right? Some students might erroneously think, oh, well, it's filled in at the 2, so it should have been the 0. But someone might say, well, it only makes sense to approach from the right side, so the answer should be set. Like, people can come up with all sorts of argument and debate. It's better to approach from the right instead of the left because, you know, the right hand is symbolic of the, it doesn't matter, right? Like, that's not, there should be no debate. So it turns out here, the limit does not exist. So you're both wrong because it's too ambiguous. Y approaches 2 values. Right? So whenever that happens, in this case, we write the limit as x approaches 2 of f of x, I say d and e, and that stands for does not exist. So when it comes to limits, we don't use the phrase defined or not defined. Oh, the limit is undefined. You can say that, but you'll sound weird. People are like, what is this problem, right? As we all know, as important as it is to know stuff, it's also important to sound like you know stuff, right? You want to sound like you know what you're talking about. So the phrase is does not exist. But it essentially means the same thing, like the limit is not defined or whatever, right? So yeah, and that is our answer here. And common error, so let me mention that while we're here. Some students may think since the hole at 2 is filled in, we have f of 2 equals 0, so the answer should be 0. But this is wrong. This comes from the idea that, oh, me taking the limit is equivalent to plugging in. If it was equivalent to plugging in, then the answer would be 0 unambiguously, but it's not equivalent to plugging in. It actually doesn't matter what the value of your function is at the point that you're looking at, right? But so that's wrong. It doesn't matter what your f equals, right? That's very important. you care about getting close to the point. And I really want to hammer that home. It is not the same as plugging in, like pretending you're there. There are a lot of differences. So an example would be, so I'm just making up a random function. So let's say you have like this is at 2. This is my function y equals f of x. Let's say here, this is at level 3, but the function is actually defined up here at level 8. And so here, the function at 2 is 8, but the limit as I approach 2 is 3. They are not the same thing. Plugging in 2 and taking the limit as you approach 2 are very different processes. They can happen to be the same sometimes. And I'm going to tell you specifically when they are the same. They'll give you the same answer. Like if this hole happened to be filled in down here, then they would be the same, right? But in general, they are not the same. And it's very important that you get that. All right, so it doesn't matter what your function equals. It doesn't matter that you're not at the point. What matters is what's happening as I get close to the point. And as I'm getting close to 2, I'm getting close to 3, not 8. Yes, the function is filled in at 8, doesn't matter, right? It does not matter what the function is, right? Okay, so that's the idea of a limit. Okay. Now, there is a concept that this thing brought up, which I want us to mention. There are a lot of limit examples to get through, as you can see. The above brings up an idea here. So in one sense, you can say, well, yeah, technically by what we're saying a limit is, there is no answer, but it kind of feels like that's cheating. Like, I mean, we do know what the y value is doing. We just believe it's doing different things on different sides. But I can tell you that on this side, it's getting close to 0, and on that side, it's getting close to 7. Like, there should be a way to express this, right? So clearly, in the above example, we can know what the y value is doing, which is the point of the limit. Remember, the point of the limit is to figure out what the y value is doing when your x value does something. So really, for someone to say D and E, it doesn't tell the full picture. Right? So this leads to the idea of one-sided limits. So there are times when overall the limit doesn't make any sense based on our definition. But from one side at a time, it does make sense. Right? So, and again, I'm going to be very intuitive here. I'm not going to give you a very technical definition, but these are the following: limit as x approaches a. But you do the following: you write a little plus sign here in the power. And what that means is the limit as x gets close to a from the right. Right? So you're approaching from the right side. And you essentially ignore the left side. And we have a corresponding notion about approaching from the left side. And you put a little minus sign there in the power of a, which, I mean, by itself, it doesn't really make any sense, but it's just the notation that we use here. So this is called the limit as x gets close to a from the left. And you ignore the right. Right, so now the idea is here we're larger than a, but let's not say we, let's be a little bit more specific. X is larger than a, but getting close to a. So it's coming from the right side. So it's not going to take on the value 2, but it's going to be 2 point something, inching close, right? And conversely here, your x is smaller than a. But getting close. So if I go to the above example and ask a different question, what is the limit as x approaches 2 from the right of f of x? And what is the limit as x approaches 2 from the left of f of x? Okay, so we can actually ask a very different kind of question. And now the answer based on the picture should be clear. I mean, here, you can see the left represents what's in red. And clearly, as we're getting close to 2 from the left, where the output is getting close to 0, while the limit as we're approaching 2 from the right is getting close to 7. So overall, the limit does not exist. But the one-sided limits do. And so that leads to an important idea. For the limit as x approaches a of f of x to exist, the one-sided limits this guy and this guy must both exist and be equal. So you can actually approach the limit idea from a two-sided kind of approach, which is actually going to be important in solving a bunch of problems later. But that is an important idea. Sometimes if you can't really figure out what the limit is doing because your function is all over the place and you don't know what's going on, take it one side at a time. And you can focus on one side at a time and see if you can figure out what's going on. So we're going to stop here, but I'll leave you with some things for next time. Not all of these examples that we saw, because I have to tell you some techniques to deal with those, but these guys, based on what I've already said, of course, I see in part C, infinity is in the mix, but just be very intuitive about it and try to tell me what you think the answer would be. So try these for next time. Tell me what you think the answers are going to be, and we'll stop there. So, yeah. So that's the concept of a limit. We'll talk a little bit more about that next time, but we are going to learn how to actually compute them quickly using strategies and formulas and whatnot. And we won't have to like draw things and like right, because that takes time. But I did that with these examples to kind of show you what the idea is, what it means to take a limit, how to know that you're getting the right answer. And sometimes you do end up in situations where you do have to just be like, what does the graph look like? Because otherwise it's very hard to figure out the answer. So you do need to remember how to graph stuff. And because sometimes you do have to get back to doing that to figure things out. So yeah, for now, that's where we will end. So hopefully that was clear. Thank you for your time and attention. I will see you guys tomorrow, same place, same bad channel. Yeah, you guys have the notes. I posted that in the chat as well as the class webpage. Be sure to email me to let me know if you did not get communications from certain sources. And other than that, I will see you guys in the next one.